co-chairman of the session, CEO, General Morris. The title of the next paper is Effects of Carrier Doping on Catalytic Performance of a Supported Metal Crystallites. The authors are M. Akubuiro of Drexel University and X.E. Verikinos and T. Ioannidis, both of University of Hadras in Greece. The speaker will be Professor Verikinos.
Since this session is dealing with issues of catalyst design, I will concentrate on the more practical aspects of a study dealing with metal support interactions, which interactions are induced by doping of the support, which is titania in our particular study, with cations of different valence. The objective of the study is to investigate the possible existence as well as the specific catalytic role of such metal support interactions which are induced by outer valent cation doping. The methodology which was followed in this investigation involved alteration of the electronic structure of the semiconducting support, titania, by outer valent cation doping, the use of these doped materials to formulate highly dispersed metallic catalysts, and determination of the chemisorptive and kinetic parameters over these catalysts under different conditions. The catalysts which were used in this study were characterized by chemisorptive titrations, by measurements of the electrical conductivity and activation energy of electron conduction, by thermally programmed desorption, ESCA, FTIR of adsorbed CO, and TEM. Doping of titania was attempted by high temperature diffusion to determine if, under the conditions employed, doping had indeed occurred. The electrical conductivity and activation energy of electron conduction of the materials was measured. As you see in the slide, when titania is doped with a cation of lower valence, such as magnesium, its electrical conductivity is reduced by approximately 1 order of magnitude. It is not altered when titania is doped with a cation of the same valence, such as germanium, and it is increased by up to 3 orders of magnitude when the parent material is doped with cations of higher valence. Similarly, the activation energy of electron conduction is reduced when the material is doped with cations of higher valence. These results indicate that under the conditions employed in this study, doping did indeed occur. The effects of carrier doping on the chemisorptive parameters of the supported metal crystallites were investigated by static adsorption of oxygen, hydrogen, and carbon monoxide. And the results are shown as the ratio of the hydrogen or oxygen or carbon monoxide to metal ratio as obtained over the doped catalyst over the same ratio as obtained over the undoped catalyst. These results pertain to platinum catalysts supported on outer valent doped titania. As you see in this part of the table, when titania is doped with a cation of lower valence or with a cation of same valence, no changes in these ratios are observed. Nevertheless, when titania is doped with cations of higher valence, then this ratio corresponding to all 3 gases is significantly reduced, indicating that under these conditions, that is when platinum crystallites are supported on higher valence doped titania, platinum loses a very significant fraction of its capacity to chemisorb these gases. The opposite was observed in the case of rhodium. As is shown here, the hydrogen to metal ratio, or rather this ratio of the 2 parameters, increases with increasing dopant concentration in the carrier. Thus, when the carrier is doped with about 0.7 atom percent tungsten, the ability of the supported rhodium particles to chemisorb hydrogen is increased by about a factor of 10. Similar results were observed in the case of ruthenium, whose capacity to absorb hydrogen is increased by about a factor of 20, and its capacity to absorb CO is increased by about a factor of 10. In addition to these changes in the chemisorptive capacity of the metal crystallites, some significant changes in the mode of absorption of these species on the metal surfaces were also observed. In the case of platinum catalysts, this was investigated by FTIR of adsorbed CO, and as you see in this table, when the carrier is doped with cations of higher valence, a significant shift in vibrational frequencies of CO adsorbed on these crystallites is observed. This shift is in the order of 20 wave numbers. A smaller shift is observed at the higher metal loading catalysts, and this, I should say, is a phenomenon which has been consistently observed in all the parameters which we are investigating. In the case of rhodium, this mode of CO adsorption was investigated by herbally programmed desorption. In this spectra that you see in the slide, the dopant concentration increases from bottom to top. Two important characteristic alterations are obvious here. First of all, the highest temperature peak is decreasing in magnitude as the dopant concentration in the carrier increases, and it is finally eliminated at the highest dopant content. The intermediate temperature peak is shifting to higher temperatures with increasing dopant content of the carrier, and the temperature shift between the 0 and the 6% doping is in the order of 80 degrees centigrade. These results clearly show that not only the chemisorption capacity of these metal crystallites is affected, but also the mode of the molecules absorbed on the surfaces are affected, the strength of the chemisorption bonds and so on. The effects of dopants on kinetic parameters were also investigated employing a number of probe reactions. I will concentrate on some results from the CO hydrogenation reaction. As we see in this slide, the specific activity of platinum in methanation and water gas shift reactions is decreasing dramatically with increasing dopant concentration in the carrier. And I'm referring to higher valence dopant. No effect was observed when the carrier was doped with a smaller valence cation. Thus, the carrier, which is doped with about 2% tantalum oxide, exhibits an activity which is about 2 orders of magnitude smaller than that of the undoped sample. The opposite was observed in the case of rhodium. When rhodium is supported on higher valence doped carriers, its ability to, in this reaction, is significantly enhanced. Both methanation and water gas shift reactions are enhanced by the doping process, and the enhancement is a function of the dopant concentration in the carrier. Here we observe a maximum enhancement in the order of 50 times or so. Another kinetic parameter which is affected in certain cases is activation, the apparent activation energy of the two reactions. In this slide, you see the activation energy observed over rhodium to be reduced upon doping. Nevertheless, this reduction does not seem to be a function of the concentration of the dopant in the carrier. Ruthenium behaved in a similar manner as rhodium. Its activity increases with increasing dopant concentration, but this is primarily for methanation and formation of higher hydrocarbons, while water gas shift activity does not seem to be affected by the doping process. Some significant changes in product distribution were also observed. As an example, I'm showing the case of rhodium. You observe in this diagram that rhodium supported on carriers doped with a higher valence cation exhibits higher activity for the production of saturated C2 and C3 hydrocarbons at the expense of the unsaturated molecules. And the same or a similar thing can be said about ruthenium, which first of all exhibits low activity for CO production and a significantly higher activity for saturated C2, C3, C4 hydrocarbons, and also it produces higher hydrocarbons as compared to the undoped sample. After carefully, experimentally eliminating some possible explanations for these phenomena, we tend to believe, or rather we propose an electronic explanation for the phenomena which we have observed. This explanation is based on the physics of metal semiconductor contacts, according to which when a metal is in contact with a semiconductor, as you see in diagram B, the Fermi energy level of the two solids must be at equal heights, which implies that if the work function of the metal, that is before contact, is higher than that of the semiconductor, in order for equilibration of the Fermi levels to occur, electrons must flow from the semiconductor to the metal, and you see the electrons right here at the interface, in order for the Fermi level to be at equal heights. This flow of electrons results in some changes in the work function of the surface metal atoms. A good kinetic probe for determining alterations in the electron structure of metal surfaces is benzene-toluene competitive hydrogenation. Both benzene and toluene absorb on metal surfaces by formation of a pi bond, which involves electron transfer from the aromatic ring to the empty d orbitals of the metal. Nevertheless, toluene is forming stronger bonds with metal surfaces because it has the tendency to offer more electrons than benzene does. As a result of that, the absorption equilibrium constant of toluene is always higher than that of benzene. So when the surface of a metal is altered electronically, if, for example, the density of states is increased, then one would expect a reduction in the ratio of the equilibrium constant of toluene to benzene. This was determined by experiments in which the benzene partial pressure was maintained constant while the toluene pressure was varied. From the slope of these lines, we can determine the ratio of the absorption equilibrium constant of toluene to benzene, and as you see, this ratio is decreasing with increasing dopant content of the carrier. This you can see better in this slide, where the ratio of the toluene to benzene equilibrium constants is plotted as a function of the dopant concentration for platinum, rhodium, and iridium. Ruthenium behaves in the opposite direction, and there is an explanation for that, which I don't have time to go over. I will close with some conclusions. It seems that altervalent cation doping of titania carriers results in significant alterations of both the chemisorptive and the catalytic properties of the supported metal crystallites. These alterations seem to depend on the specific metal, on the metal crystallite size and surface density. This is actually, I have not shown, and on the doping cation and its concentration in the carrier. The phenomena observed are probably due to long-range electronic interactions at the metal semiconductor interface, and I should probably add that these interactions, which are induced by doping of the carrier, could be used to alter the activity and the selectivity of metallic surfaces in a desired direction. Thank you.
Two quick questions. Go ahead. Identify yourself. Okay.
University of Illinois at Chicago. In the cases where you're using tungsten trioxide, have you taken into account the spillover of hydrogen from the metal to the trioxide and the formation of the hydrogen bronze?
If they can absorption of hydrogen,
The spillover of hydrogen from the noble metal to the trioxide
yes.
and the consequential formation of the hydrogen bronze, that can account for a lot of the additional
Yes.
hydrogen uptake.
Okay, I must say that the concentration of tungsten within the carrier is in the order of maximum 0.7%. So there isn't much tungsten on the surface or in the neighborhood of metal crystallites so that for spillover to take place. And this we have verified by ESCA analysis. Furthermore, we have these results that I showed have been obtained by two techniques, one of which is the dual isotherm technique, which would have indicated if such spillover had occurred, and we have not observed that.
One more question.
Alex Bell, University of California, Berkeley. Experiments done with monocatalyst systems, specifically with rhodium, have shown that many of the effects on CO hydrogenation can be explained by titania overlayers, partial overlayers on the surface. It's also conceivable that in your type of experiments these overlayers exist and that the overlayer in fact is modified by tungsten or titanium.
Yes.
Why do you exclude that as a possible explanation?
Okay, I exclude it not from the data that I have just shown, but it is known that these overlayers disappear when the samples are exposed to oxygen.
Not completely.
Well, to a large extent.
No, they don't.
I think the literature shows that this SMSI phenomenon.
That even at low temperature reduction and after exposure to water, the promoter effects of the support are still evident.
Okay, I guess we are getting deeper into the subject. So. We have to move on.